Hello everyone. Today we will continue discussing our topics on synchronous machines. So in the last session we finished and solved some examples on the synchronous generator, and we understood the constant power operation of the synchronous generator. Now we will discuss the synchronous machine in the motoring mode. So as we agreed before, the same machine can work as a motor or generator. It depends on the power flow direction. So if we are going to convert electrical power to mechanical power, so this means the machine is in the motoring mode. And if we are going to convert mechanical power to electrical power, so this is going to be the generating mode. So the same machine without any like physical changes, it's going to work as motor or as generator, depends just on the power flow direction. Okay, so let's figure out firstly the operation and troubles we have, these troubles we have in the synchronous machine operation. So, in the synchronous motor operation. What is the trouble we have? So, like any motor, guys, when you supply the motor, you need the motor to start rotate. You need the motor to carry the load, the mechanical load, and start rotating, like any device you have at home. Okay. However, the synchronous motor, if you just brought the same synchronous machine, which is working as a generator, and connected the AC supply in order to allow this machine to rotate, it will not rotate. And this means it's not a self-start motor. So why it's not a self-start motor? This is what we need to figure out. And at the same time, if it is not a self-start motor, how can we start this motor? So for DC motor, for instance, guys, we learned that once you start the motor, so if you just apply the field to the field winding of the DC motor, if it is field-based machine, like shunt or separately excited machine, for instance, or if it is permanent magnet, so the field is already inside. So once you apply the DC source or the DC supply to the armature winding, the machine will start rotating. But this is not the case in the synchronous motor. Why? Let's investigate together why this is the case in the synchronous motor. In order to understand that, firstly, guys, we need to remember that our synchronous speed relation, which is NS equals 120 times frequency of the supply divide number of poles. So this is the synchronous speed of the motor. Normally, this synchronous speed also is the mechanical speed and field speed inside the machine, which means if I have the three-phase machines and I supply the three-phase supply to the armature winding, the field will rotate in the air gap with this speed. Okay. So if you imagine with me now in this figure, I'm going to assume that you have a pole, which is when we supply the motor at one time t, let's say at t equals 0. So the pole on this side is N and in that side is S. And with time, this pole or this pair of poles will start rotating. So if we have a supply of 60 hertz and number of poles is 2, so in this case, if you substitute here in the relation, you will find that the synchronous speed is 3600 RPM. As we mentioned before, guys, the synchronous speed has some definite values. So it's a good chance also to discuss this point, because as you can see here, number of poles cannot be a fraction. It has to be a real number, and a multiple of 2, it has to be even number. So 2 poles, 4 poles, 6 poles, 8 poles, and so on. So number of poles has to be an even number. So if you can imagine with me now, all supply frequencies around the world is 50 hertz or 60 hertz. So this is the frequency. And number of poles can be 2 poles, can be 4 poles, can be 6 poles, and so on. So in case of, let's make this table together. In case of 2 poles, if you multiply here, use the 50 hertz and P equals 2. So what would be the synchronous speed in case of 2 poles here as well? In case of 4 poles, in case of 6 poles, and you can continue make this calculation. So what would be the synchronous speed? So let's write that in a different color. So if you use this relation here now and substitute, so 120 times 50 divided 2, this will lead to 3000 RPM. So if the number of poles is 4, so this number will be 1500 RPM. If the number is 6, so you can continue multiply and get the value and so on. The same here, 3600, 1800, and so on. I believe here 1200 and so on. So this is the way, guys, how we can calculate the synchronous speed. So if the machine is supplied by 60 hertz, we don't have synchronous speed, for instance, equals 2000. It's impossible because number of pole has to be 2 or 4 or more. There is no fraction pool between 2 and 4. So there is no speed between 36 and 1800 for the 60 hertz machine. And the same is for 50 hertz machine. If the supply is 50 hertz, so you don't have synchronous speed between 3000 and 1500 RPM. It's impossible. Okay. So for that, guys, synchronous speed are some definite numbers. It cannot be any variable speed. Only it can be variable if you make the frequency variable. And this is possible if you have variable speed drive, which change the supply frequency. So you can have whatever frequency you need in order to make speed control with different values. Okay. However, if you have the normal supply, we have at home 60 hertz. So the machine speed is going to be with these numbers only. Okay. So this is something unique for the synchronous motor or synchronous machine in general. Okay. Induction motor and DC motor are different. We can have different ranges of speed. For that, guys, we call this machine synchronous. Why it's synchronous? Because the machine speed is synchronized all of the time with the supply frequency. So again, let's go back to our discussion about the motor. So once you supply the frequency 60 hertz, 3-phase supply to your motor, at a certain time, we would have this pole in this position, and this should be rotating with the synchronous speed, which is 3600. Now, let's imagine with me that due to the DC supply you have on the rotor, you know that, as we discussed earlier, the rotor of the synchronous machine is supplied, the winding of the rotor is supplied by DC source. So you would have constant flux like that. Okay. But because the AC supply or the armature winding is supplied by AC, so this number of poles or these poles are gonna rotate, okay, or change at the same position, or this pole is gonna move according to the direction of the rotation. So assume that you have here S pole and N pole for the rotor. So let's focus on this side of the rotor right now. So this is S. And you have at one instant now, you have N at this side. So the logic operation is this pole S is going to be attracted to pole N. Why? The nature of the field lines, the field is going to move from N to S and then move through the rotor and return back to S like that. So this is the flux path. And you know that the features of any flux line it leads to reduce its length. So if it needs to reduce its length, it will attract this pool in order to be in front of the N exactly here in order to have the minimum path, which is required to be like that, for instance. You know that the mechanical time constant, we discussed that in our last lab in DC machine, and discussed the moment of inertia of the DC machine, and we discussed the mechanical time constant. So the mechanical time constant, all of the time, guys, mechanical time constant is much more than the electrical time constant of the same system. What does it mean? If you have a motor, and let me describe it when you turn off the motor supply. So when you turn the motor supply off, the motor is not going to stop immediately. It will take some time to be turned off because there is stored energy inside the machine, and this stored energy needs to be dissipated until stopping the motor. So this is called now time constant or mechanical time constant. So the mechanical time constant of the motion of the motor is much higher compared to electrical. How can we recognize that? For instance, if you have a light and you disconnect the supply from the light, so the light is going to be disconnected immediately. It will not take very long time like a motor to stop. For that, the mechanical time constant is more than electrical time constant. And by the way, thermal time constant is much higher compared to mechanical and compared to electrical. For instance, if you boil some water to 100 Celsius degree and disconnect the source of heat, so it will take very long time until this water turns cold or turns to regular room temperature. Okay, so for that, thermal time constant is much larger than mechanical and also much larger than electrical time constant. So again, so the flux lines here try to move the rotor toward this pool. But this is not fast enough because this is mechanical system. And the supply is going to be changed very quickly because this is electrical system, which means this pool will be turned to S, and this S will be turned to N in very few milliseconds. So what will happen is the S pool will make repulsion force with the S pool of the rotor, which means instead of moving the torque in this direction, there will be an opposite torque moving to the other direction, which is this case right now. So here at t equals 0, here at t equals 1, what happens is the motor will, or the rotor will start or will have a force or torque to move it in the opposite direction. If it starts moving to the opposite direction, this pool will change again from S to N and can return to this case again, which means now our rotor is not going to start. The motor will not start. Why? Because the pool changing of the stator, the polarity of the pool of the stator is very fast compared to the mechanical motion of our rotor. For that, the synchronous motor is not a self-start. So, does it mean we cannot start it? For sure, no. We have motors already and it's working. So there should be a way or more to start the synchronous motor. So what are the different ways that we can start the synchronous motor? Actually, all of the ways are coming from the same concept, which is because the electricity speed is high and the mechanical speed is low in the transient period during turn on, we need to reduce the the supply frequency, or let's say in another word, let's say we need to have small relative speed between rotor and stator poles. So in the beginning of the motion, the motor is at standstill, which means has zero speed. So this is 0 RPM. And here the field is 3600 RPM. So the relative speed is nothing but the difference between the two speeds, which is 3600 in this case. So this means the relative speed is very big number, very high number. So we cannot start the motor by this way. The way to start the motor is to make smaller relative speed. How can we make relative or smaller relative speed? We have two different ways here. A first way is to reduce the speed of the field. How can we do that? You know that this synchronous speed depends on the frequency. We're not going to change the number of poles for sure to control the speed right here. Okay. However, there is a way to make pole changing to control the speed, but this is not in synchronous machine. This is in another motor, and we'll discuss that in the induction motor later on. But for the synchronous motor, we don't change the number of poles. So the factor that we can change here is the frequency. If you remember a few moments ago, I just said you can control the frequency using variable speed drives. So what we can do is you can start with very small frequency, like 1 hertz. So 1 hertz, for instance, means the supply, the AC supply time is going to be 1 second because this is 1 hertz. So this means we will have half a second in positive half cycle, which means this N will stay in this place for half second, which means this pole will be easily move and catch the pole of the stator. And once the poles have been aligned together, so this motor will start without any problem. Okay, guys. So this is the concept now. So we can do that by reducing the frequency of the supply. So a first method is starting at reduced supply frequency. How can we do that? Using variable frequency drive. We call it VFD or VSD, variable speed drive or variable frequency drive. What is the variable frequency drive or variable speed drive? This is nothing but a power electronic device. This device converts AC to DC and then DC to AC with variable voltage and frequency. So we can have a supply with very small frequency in the beginning just to start the motor. Once the poles are aligned, the rotor or the stator flux catch the rotor. So in this case, you can increase the frequency because there is a zero relative speed between both of them. So it can rotate even with very high speed in this case. It's like, guys, if you would like to catch a bus. So if the bus is moving with very high speed, you cannot do that. But the bus has to stop or at least has to be slowed down in order to catch this bus. Once you catch the bus, you enter the bus, we will move with the bus with the same speed. So this is the concept right here if you started with reduced frequency. This is the first way. The second way is start as induction motor. It's a bit tricky because we didn't discuss the induction motor, but I'm going to give you just a quick discussion how the induction motor starts. Okay. So the induction motor, guys, has something called Dunbar winding. So these are the two methods that we just discussed. So this is a variable frequency technique, and this is the variable frequency drive that we just mentioned. Okay, we call it sometimes also frequency converter, but this is not the industry name we give it for this device. The name is variable frequency drive or variable speed drive. The second method is starting as induction motor. How? The induction motor, guys, has a rotor like that. We will discuss the induction motor in the next topic, okay? But for the time being, we need to know that we have like a cage inside the rotor. What the cage means for us? So the cage means we have like rotor bars, and these rotor bars are shorted from both of sides. This technique allows the motor to start automatically. And we call it here, if we install this cage on the rotor body of the synchronous machine, we call it damper winding. So this is damper winding, okay, or cage that we install on the synchronous machine. Okay, so what is the concept? How this motor is starting? So I'm not gonna discuss in more deep how the induction motor starts, but you need to know that the induction motor is a self-start motor. So once you supply the three-phase induction motor, it will start with a speed called rotor speed, and this rotor speed is very close to synchronous speed at no load. Very close by a small value called slip. So NR equals 1 minus S times NS. And this value is called slip, and this slip is very small value. It can be 0.01, so just 1%. So this means the rotary speed is going to be very close to the synchronous speed. This is a function of the induction machine. I'm not going to discuss here today how the induction machine starts working. This is in another topic, but you need to know that the induction motor, for the time being, you need to know that the induction motor is a self-start motor, and it rotates with a speed very close to the synchronous speed. Now let's go back to our diagram here again. Let's say the induction motor is rotating with, instead of 0 RPM, we have, for instance, the induction motor is rotating with like 3550, 3550 RPM. So this means the relative speed is 50 RPM, which is a small value. In this case, if we supplied our machine here with the AC, but don't connect the field winding. Don't connect the supply to the field winding. So in this case, you would have no polarity. It's going to be just a piece of iron. And the concept of the piece of iron is, if you have pool here, so the flux line is going to be the same moving through the pool here, and it will try to reduce its length or its path, so it's going to move this rotor toward the side. So even if you have just a piece of iron, you can do that, okay? So in this case, we will not connect the supply to the field winding and supply the stator winding by the three-phase AC source with the same frequency. So what will happen is the machine is going to start as induction motor with this speed. Once we have this speed, guys, connect the supply with the field winding. So when you connect the supply to the field winding, now you will create the pools. So in this case, the relative speed is going to be very small, and it can catch the field of the stator. It can catch the rotating field, and in this case, it will continue rotating with the same speed, which is 3600. So the concept again for starting as an induction motor is, firstly, we have the cage or the damper winding. So the damper winding is going to start the motor as induction motor, and once the motor starts rotating, connect the field winding of the synchronous motor. So what will happen is the speed is going to increase from NR to NS, and the machine will rotate with the same synchronous speed. So this is the second way how can we start the induction motor. Sorry, the synchronous motor. So the first way is to start by variable frequency using variable frequency drive, and the second way is to add the damper winding, which is going to start the machine as induction motor, and then connect the field winding so the machine is going to move with the synchronous speed. If you didn't connect the field winding, so the machine is going to work just as induction motor, not as synchronous motor. Okay. And again, regarding how the induction motor works or start, this will be discussed in more deep details in the next topic. Okay. Now, in terms of the mathematical model and the phasor diagram, we need to drive that also for the synchronous motor as we made for the induction motor. Let me create one more slide here. So our circuit, as you remember, we have this is the excitation, this is the armature resistance, this is the synchronous reactance, and here we have the motor terminal, this is V terminal. So this is the equivalent circuit of our synchronous machine. It's going to be the same for sure. So the equivalent circuit is the same for the same machine. But what happened in motoring mode is the current is entering the machine instead of going out of the machine. So this is the direction of the armature current. So since the current is reversed compared to the generator, we can apply here Kirchhoff voltage law right now, and we can say that V terminal equals EA plus IA times RA plus JXS. So you can say also EF, or sorry, EA, whatever AA or F, guys, okay, equals, I think we have it in the symbols here, EF. Okay, so let's change that to EF. So EF equals V terminal minus IA times RA plus JXS. So this is the equation of the synchronous motor. How can we draw the phasor diagram of the synchronous motor? You remember, guys, in case of generator, we mentioned that the power factor of the generator is load dependent. So in case of generator, power factor depends on load. So the load itself can be inductive load. So the power factor is going to be lagging in this case. And it can be capacitive load. And the power factor in this case is going to be leading power factor. And it can be also resistive load. And in this case, the power factor is going to be unity power factor. This is in case of the synchronous generator. In case of motor, someone can say motor is a motor, which means we have some windings, so it's like supplying an inductive load. But actually, in the synchronous machine, the concept is a bit different. Why? Actually, this because we have an internal source inside the machine. So the induced voltage inside the machine itself play a role in controlling the power factor. Which means by changing the value and phase shift of the excitation volt here, this can control the power factor of this machine. So still with the motor, we have the different cases. So the motor can work also with variable power factor. So this means also we have the three cases like we have in generator. So let's see a first case, guys. I'm gonna say, let's see the lagging case. I'm gonna make the phasor diagram by the same way. So this is V terminal. Again, guys, I'm drawing here without roller. So you should use your roller when you draw the phasor diagram. It shouldn't be freehand. Okay. So if the V is our reference, as you can see, and this is the way also all of the time we draw the phasor diagram. So V at angle 0. And I'm gonna assume that our current is lagging like that. And the same angle here is the phase angle of the power factor. So this is the first case, lag. Let's make the same rule and draw the phasor diagram in case of motoring. So I'd like to get EF. So the relation is VT minus IA times the impedance. We can make it now like that. VT minus IA RA minus JIA times XS. This is V. So this is the first term of the phasor diagram. Now I need to make the vector minus IARA. IA is a vector, RA is a scalar value. So if this is the direction of IA, so minus IA is going to be the opposite direction like that. So this is here minus IA. So the vector minus IARA is going to be in the direction of minus IA. So I'm going to say this is minus IARA. Then we have minus JIAXS. J is, this is IA again, so J is in this direction, so minus J is going to be in the opposite direction. So this means the minus J IAXS is going to be like that. So this is minus J IAXS. So this means the resultant vector is going to be in this direction. So this is EF in our machine right now. So this is the lagging operation. If I neglect the armature resistance, so I'm going to draw the phasor diagram with you again in case of RA neglected. So this is V terminal. This is the lagging IA. So again, this is minus IA. So the minus JIAXS is going to be in this direction. So this is minus JIAXS. So this is going to be the EF. So this is the first one here in case of RA considered, and this is RA neglected. So this is the phasor diagram in case of lagging power factor case. Let's see that on the next slide here. So as you can see here, guys, this is the case of lagging power factor that we discussed. In case of IARA is here, this is minus GIARA, and this is EF. If you make unity power factor, so unity power factor means IA is in phase with V. So this is V, this is IA. So minus IARA is going to be in the opposite direction. So this is IARA, and the minus IARA is going to be here like that. And then minus JIAXS is going to be in this direction. So this is EF. And in case of leading power factor, so this would be the case. So you can drive the leading power factor by the same way. So these are the three cases of the phasor diagram we have in the synchronous motor case. What can we observe from the three phasor diagrams in the three different cases here? Our observation can be, for instance, if you have a look to the power angle delta, you will find that the power angle is negative in the three cases. So this is the first observation here, all cases the power angle is negative. What is the meaning or what that reflects? The meaning is the power angle is a sign of the power flow direction. So in generating case, the power angle was positive, which means the machine is generating electrical power. In case of motor, because the power flow is reversed, the electrical power is supplying the machine. So this means the power angle delta is going to be negative. So it's like basics, guys, for the synchronous machine. Basically, the power angle is going to be positive, so this is generator. If the power angle is negative, so this is a motor. So you can figure this out in any question, in any solved example, in any problem you solve. If the calculations makes the power angle negative sign, so this is motor operation. If the calculation makes the power angle positive sign, so this means it's generating operation. If you find the opposite, so something is wrong. I mean, if the machine is working as a motor and you got the power angle in positive sign, so something in your calculation is incorrect. You have to repeat your calculations again. So this is the concept of the power angle. Now, another observation we can get from the phasor diagram here. If you find the relation between the excitation and power factor, you would find that here the power factor is leading and the excitation is, as you can see, the excitation vector is high compared to the other two cases. In case of unity power factor, this is like the normal operation case, or we call it normal excitation. And in case of lagging power factor, it's smaller, so we call it under excitation. So we have now leading power factor is over excitation, unity power factor is normal excitation, and lagging power factor is under excitation. Actually, this is the opposite to the the synchronous generator case. So in order to make it easy for you, because you have many cases now, let's write this technique together. So I'm gonna create a slide and another note here, another slide. So let's see, do that here. So in case of lag generator, the excitation was over excitation. In case of unity power factor, guys, motor or generator, it's gonna be normal excitation. This is not confusing. But in case of lag and generator, it was over excitation. So let's memorize only this. And if you'd like to change any term of the three terms, you have to change 2 out of 3. Which means, if I say lag motor, so I change just one right now, so I have to change the other. So this is gonna be under. So if the motor is lagging, so it would be under excitation. If I said lead motor, so I changed 2 compared to here. So instead of lag, I made it lead. Instead of generator, I made it motor. So we changed already 2 out of 3. So you have to keep the remaining term. So in case of lead, in motor case, it would be over excitation. So this is the way, guys. So this way is easy way to memorize this one, because we will use these expressions in our numerical problems. So in the question, you would have some signs to say the power factor is lagging or leading. So instead of saying for you the motor was working in leading power factor, we can say, for instance, the motor was overexcited. So once you know its motor and overexcited, so this means it's leading power factor. Okay, so you need to memorize these three words, and if you would like to change, you have to change 2 out of 3. Okay. Okay. So these are our observations from the phasor diagram of the synchronous motor. What about the power factor controls? Do we need to make power factor control for the synchronous motor? Actually, this is very important. So let's go here and discuss one thing, guys. Imagine that we have a power system, or you have a supply in a factory, for instance. So this is a factory getting supply from a transformer, and this is a bus bar. And you have here some loads. Load number 1, load number 2, load number 3, and so on. So most of our loading in industry are inductive loads. So this is a nature of our grid. You have motors, you have transformers, you have a lot of devices that absorb reactive power. So the majority of our loads are inductive loads. Even the loads that have some power electronic devices or power supplies that converts AC to DC, still it has lagging power factor because there is a phase shift between the generated DC and the AC makes the power factor is lagging all of the time. So the normal or the majority of loads in our grid is inductive load. Inductive load means the reactive power is coming from the supply side to the load side. Now imagine if you have one of the loads here is synchronous motor. So synchronous motor can be controlled now to have leading power factor. So leading power factor means that synchronous motor can provide reactive power. So if I can say this is Q coming from the supply to the different loads, the synchronous motor is the only device that can work to deliver reactive power. So this means we can have our mechanical load. So the synchronous motor will have a certain apparent power. And you know S equals P plus or minus JQ. This is the regular equation of the apparent power. So with the same mechanical load, because mechanical means it absorbs active power. So with the same mechanical load on the synchronous motor, we can control this term to be positive or negative, or let's say in another word, to be delivering reactive power or absorbing reactive power. If the synchronous motor is lagging power factor, so it will absorb reactive power. If it is leading power factor, it will deliver reactive power. And the load is independent. The load means the active power is independent. We don't care about the reactive power right now. Okay? So the question is, why not making this synchronous motor working at leading power factor mode to deliver some reactive power to our loads? What is the concept? Why do we need that? Actually, we need to do that in order to reduce the amount of the reactive power absorbed from the supply. And this would improve the overall power factor at the bus bar. And you know that from electrical circuit, guys, you know that if you improve the power factor, this will reduce the current absorbed in this cable. This would reduce the stress on the transformer. This would reduce your electricity bill. You will not have like penalties because of the power factor. So all of these are benefits. So we do need to make the synchronous motor working at leading power factor. Why? Just to support the surrounding loads by reactive power and improve the power factor at the entrance of our factory. Okay. So this is one advantage of the synchronous motor. We can use it. Another question. Someone can say synchronous motors are very little now in industry. It's not used a lot like before. And in most of factories, we have these motors like in stores, and we don't use it anymore. So in this case, you can get the benefit of getting that motor from the store and connect this motor to the supply without having any mechanical load and just run this motor at leading power factor. Is it gonna absorb active power from the grid? It's gonna absorb just the amount of active power that will be consumed in the motor losses. So you remember that if the motor is working at no load, so we still have some core and copper losses. So we have P core and P copper in the synchronous motor. But this is going to be small value. Core loss is constant. Copper loss is load dependent. It depends on the amount of current you will absorb. Okay. So if you have the motor working at no load, so in this case, guys, you would have smaller losses. And mostly, if the synchronous motor is high power motor, so this amount of loss is going to be very small because the efficiency of this motor is very high. Okay. I'm going to elaborate more, guys, in the copper loss of the synchronous motor compared to induction motor, but not today. I'm going to elaborate more in this point when we start discussing the topics of induction motor, comparing the efficiency between synchronous motors and induction motor. We will find that the induction motor is less efficiency compared to the synchronous motor because of copper loss. So the copper loss in the synchronous machine is less than the copper loss in the induction machine. Okay, this is because the rotor is moving with the same speed, which means we have zero copper loss on the rotor side. Okay, zero copper loss compared to the induction machine. So the copper loss in the rotor side is going to be just the field effect. So we don't have the same AC losses that we have in the induction motor on the cage or on the damper winding. Okay, so again, if I operate this motor at no load, so I can say that P is going to be very small. And in this case, I can have the complete value of S as a reactive power. So if I take this motor from the store on shelves and just connect this motor to the supply and controlling the power factor of this motor to work as lead, so I can have almost the Q equals S if we neglect the losses numerically. If we neglect the losses, so Q is going to be the same as S, and this motor will provide reactive power and work to compensate or improve the power factor of my system. Okay, so this is very interesting thing in the synchronous motor. So if you have it and working with loads, you can control the power factor to support the reactive power or support the power factor. And if it is even not working at all, you can just connect that to supply in order to provide the whole capacity of apparent power, okay, as reactive power, and this would improve also the power factor. Okay, so this is one of the advantages of the synchronous motor compared to any other motor like induction or synchronous motors. Okay, so I mentioned now many times control the power factor, control the power factor. How can we control the power factor now? So if we compare the three cases of the phasor diagram, so here we have the first case, EF1. This is at IA1, which is lagging to the volt here. EF2 is due to IA2, which is unity power factor, and EF3 is due to IA3, which is leading power factor. If you compare this phasor diagram with the constant power operation of the synchronous generator, it would be just like a mirror across the terminal volt. So if you make a mirror for this phasor diagram, it would go to the upper side, and this would be the case of synchronous generator. If we go back a few slides to show you that again here. So this was the constant power operation that we discussed previously in our class. So we just mirror the phasor diagram across VT because just we convert the current. So we just oppose the current direction. So this is why it's like a mirror across VT. So this means, guys, we can say from here, or we can conclude from this phasor diagram, if we control the excitation value, and we can do because excitation is the DC source, or we can control the excitation using the DC source that supply the field winding, and this is accessible. We can control that using variable DC supply, for instance. So if we control the excitation, we can control the power factor. Because if the motor is lagging at EF1, at small value of excitation, let's increase the DC supply. If we increase it to the EF2 value, so the power factor is going to be unity. If we increase that to EF3, so the power factor is going to be lead. So simply you can control the power factor using excitation. Okay, so if we draw the relation between the excitation and power factor, so we can end up with this curve. Let's see this curve together, guys. Here I have IF1, which was lagging case. So this is going to be lagging case. Here I have IF2, which is due to the unity power factor case. So this is unity power factor. Here we have IF3, which is due to EF3, which is the leading power factor. So this is leading power factor. And the power factor curve is this one. So here, the power factor value was small. If you increase the excitation, so the power factor is going to increase until having the maximum value, which is 1 at the unity power factor case at IF2. And then if you increase the current again, so sorry, if you increase the excitation again, so it will convert to lead, which means the power factor is going to reduce again. The power factor of the motor, not the power factor of the connected loads in case of power factor compensation. So I don't care about the power factor of the motor now. I'm caring about the power factor type. Is it lagging or leading? Okay. I mean, the target is to improve the power factor of the overall system, not to improve the power factor of the synchronous motor itself. Okay. I just care to have leading power factor in order to get the maximum reactive power from my synchronous machine. So this curve, guys, is the power factor relation with the excitation. If we compare the current magnitudes IA1, IA2, and IA3 in this figure, you would find that IA2 is the minimum possible value, correct? If you compare this current for the three cases, you would find that IA2 is the minimum. And this is all of the time going to be the case in unity power factor. So if I say minimum current, I mean by current, the armature current. So this means it's equivalent to unity power factor. So this is one important note. We can get it from this phasor diagram. So if I said I control the synchronous motor reactive power and I made minimum armature current, so this indicates that power factor is unity. So these expressions are very important, guys. So I control the armature current to be minimum. This means the power factor is unity power factor. So as you can see here, we draw also the current curve. So this is IA, and this is the excitation. So the minimum current is going to be corresponding to the unity power factor at the same IF, okay? And here is the value of current in case of lagging, which is IA1, and here is the value of IA3. This curve, we call it V curve. V curve. So V is representing the armature current versus field current. So it's not volt, but we call it V curve because the shape of the curve is like letter V. So this is going to be now, guys, the power factor control of the synchronous motor. Actually, if you change the loading condition, which means change this value or that value, so this means the power of your machine, because this value here is representing IA times cosine phi, which is power factor, and this value here represents EF sine delta. So the power is proportional to these two terms. You remember that power equals EF V terminal divide XS sine delta if we neglected the RA. So this means if VT and XS are considered as constant all the time, so power is proportional to EF sine delta. And the same is also the same electrical power equals V terminal times I times power factor. So V is constant, so it depends also times, it depends on I times power factor. So if we change the motor active power, so this curve is going to change with us, and the curves are going to be like that. So the line of the power factor or the unity power factor is going to be moved in this direction. So this is the unity power factor curve, or the locus of unity power factor at different power cases. And this is called the curve of a synchronous motor. We will make one experiment on the synchronous motor and drive and provide the different V curves at different power conditions. Okay, so this is one of the experiments we're going to do together in our lab. Okay, so this is called power factor control, or V curve. So if I ask you a question, guys, in the exam, the V curve is a relation between the excitation volt and terminal volt, excitation volt and armature current, excitation volt and field current. So you can say it's excitation volt with armature current. Why excitation volt? Because excitation volt is going to be proportional to the field current. So we can say it's a relation between IA and IF, or IA and EF. Any of these terms are related to each other. But if I say VA, the terminal volt, so this is incorrect. So the V curve, the name comes from the shape of the curve. It doesn't mean it is a voltage across a motor. So this is important note we need to know. Okay. I think we don't have more time right now to solve this example, so we will start next class with this example together. Thank you so much, guys, and see you in the next class.